I'm going to talk about why clean code means good code. What is clean code? In some circles on the internet, you're going to hear it's over-engineering, piles of useless abstractions, tiny methods and classes that obscure the flow of control, and horrible performance. I'm going to argue these things are bad code, and clean code is always good. And we should use clean code to mean good code. Robert C. Martin wrote a book in 2008 called Clean Code. He followed it up with clean architecture, clean agile, clean craftsmanship. Together, these books total 1,500 pages. This is one reason why I'm going to argue clean code has become a cliche that doesn't really mean very much. Because when I see summaries of what clean code is, it's usually 5 or 6 simple rules, when he wrote a full 1,500 pages on the subject. I only have the first one of these books, Clean Code, so I pulled it off my shelf. Consider this book a description of the Object Mentor School of Clean Code. What is Object Mentor? Object Mentor was Uncle Bob's consulting company that he started in 1991. They focused on object-oriented technologies, including Java, where Java is arguably the most object-oriented language. Also in Chapter 1, he said there are probably as many definitions of clean code as there are programmers. He contacted several well-known programmers and asked them, what does clean code mean to you? Bjarne Stroustrup, clean code is elegant, efficient, and straightforward. Grady Booch, clean code is simple and direct. Dave Thomas, clean code can be read and enhanced by a developer other than the original author. I like that one. Michael Feathers, clean code looks like it was written by someone that cares. I searched to see what early references of the phrase clean code I could find. This one from 1986 provides no help whatsoever to aid the programmer in writing clean code. This one from 1989. You start the day with, say, 1,000 lines of crappy code, end of the day with 300 lines of clean code. This was almost 35 years ago, and it sounds like something you might hear today. I'd go as far as to say clean code has become a thought-terminating cliché in some circles. It feels like the sides are already drawn. People know whether they are for or against clean code, and there's rarely any productive conversation. So I'm going to try to diffuse this bomb a little bit by taking a couple steps back and just offering a wider perspective on the subject. Casey Muratori, who used to work for Rad Game Tools, making game libraries, he worked as a programmer on The Witness with Jonathan Blow. He has content, both free and paid. I think in general his content is really good. I'm going to focus on one post he made that I think was a little heavy-handed or a little one-sided. I've heard him talk about this post with other content creators. If you write an extreme and kind of hyperbolic take, you can get a lot of attention. So he got a lot of attention for this post. I think it's good. He was driving traffic to his performance-aware course. I think he's a good educator, but I do want to respond to some of the things he said. In the post, he makes a comparison between two implementations of the same relatively simple calculation. The calculation is in a corner-weighted area of a bunch of shapes and summing it up. So it's a made-up calculation, but I think it's valid. It proved to be interesting. I would call this a classic intro to OOP solution. Like, this is a vanilla OOP implementation, which I think is very fair to make a comparison with. He has a base class here that's an abstract base class because it has 2 pure virtual methods with no implementation. And then he has 4 concrete derived classes: square, rectangle, triangle, and circle. Each one implements both of those virtual functions. And then in the loop body, when he's looping over the shapes, he calls both of those and does a little math with them. Jumping ahead to his optimized version, there's no more base class, there's no more concrete classes, there's no more virtual functions. Instead of the 4 derived classes, he has an enumeration that lists the 4 shape types. And then he has a single struct that carries the data for those shape types. The shape union struct has a width and a height. We'll see later that this width and height don't totally map onto the original shapes, but as an optimization, it works very well. Next, he has this lookup table. He combines the constants from the virtual functions with the constants from the loop body. And he makes the observation that we're just multiplying these things together over and over. So in the optimized version, he creates this lookup table. He does the math once up front, probably at compile time. And then in the loop body, He just has to do a lookup into that table, and then he does 2 multiplications. In a final step, he adds in some AVX instructions to vectorize this loop, so it's doing more work in parallel. He doesn't actually show that version of the code because I think it would look a lot like assembly language, but it's a totally valid optimization you can do when you have a loop that's written like this. In this first row, we're going to look at the performance numbers from his post. The other 2 rows are just simple arithmetic on those numbers. Let's just assume it's a 3 gigahertz processor, multiply it out. Those numbers are so extremely small, sometimes it's useful to transform them. Let's look at the number of shapes processed in 1 millisecond. Again, it's just 20 times, but this is another way to think about it that's a little more intuitive depending on what you're doing. I'm going to talk about 2 big reasons his version is faster. The third reason would be the AVX instructions. The first one is the memory layout. This is the optimized version first. We have the enum, we have a single struct for all the shapes. We're processing a pointer to the shape union struct. That means we have an array, and in every array slot, there is a shape union struct, a dense array of contiguous memory. This is so fast and so preferred by computers that I think a lot of times we don't even talk about it, especially if you're new. This is ENIAC from the 1940s. And from the earliest days, what computers have been designed to do most effectively is walk through a dense array of contiguous memory. Everything from the CPU to the RAM to the caches, everything is designed to be most efficient when you're walking through this array. You just have to realize how important memory layout is. In the OOP version, we have an array of pointers. This is actually a little misleading because this is implying that the shape-based objects are in a parallel array, that they're nice and neatly arranged. This is kind of a fantasy. This is not generally what you'll see. Instead, what you see is something like this. So if you think this is an exaggeration, it's actually not. In a real application, you're probably going to be allocating these shapes at different points in time. Even if you don't do that, at some point you're going to filter this array, you're going to sort this array, you're going to do something with the array. And because it's decoupled from the locations of these objects in memory, you're going to end up with a mess like this. The code might be clean, but the memory is messy. One way to think about it is an object is an abstraction. I want to create this object. I don't care where it lives. I want to access this object. I don't care where it is. That works great at certain timescales, as we're about to see, but it works horribly at other timescales. After memory layout, the second biggest concern here are the virtual functions. Just looking at them, I can already tell you the virtual functions are way too small. A lot of abstractions in C++ are what they call zero-cost abstractions, but virtual functions are not zero cost. Plus, you're going to get hit twice. There's going to be the runtime cost of looking up the method, and there's also the cost that now your inner loop has this uncertainty about where the instruction pointer is going next. And that makes it difficult for the compiler to optimize and difficult for the CPU to run it efficiently. Here's my depiction of a virtual function that's not carrying its weight. It's not doing that much work. If that was the end of the story, if we had an OOP version that was slow and an optimized version that was 25 times faster, just always do the optimized version. But there's more to the story. In his shape union class, as you can see, the only data members are a width and a height. He's already kind of muddied the data model because circle, it has a radius. So he'll just stuff that radius in as the width and the height. And a square should have just a side, but he will put that side in for the width and the height. So you can already see there's some cracks here. This is fine. If these are your only 4 shapes you're ever going to have, this is a reasonable optimization. But if this is just the beginning, if you're going to be adding things like a polygon with end sides, if you're going to have curve patches, shapes swept along a spline, 3D shapes, the advantage of the OOP version is that each concrete type can have its own data. The data can vary arbitrarily from one concrete type to another. Therefore, the function implementations can vary arbitrarily. He's taken advantage of the fact that the data in the 4 original shapes are very similar, and the area calculation in the 4 original shapes are very similar. Again, that's a totally valid optimization, but it might fall apart if you're going to add new shapes. After presenting his optimization and showing that it's 25 times faster, what does Casey conclude? He concludes that the clean code rules simply aren't acceptable, that the clean code rules are almost all horrible for performance and you shouldn't do them. and that the clean code rules need to stop being said unless they are accompanied by a big old asterisk. Is Casey right or is he wrong? I think that Casey is exactly right and exactly wrong, and it just depends which case you're in. Let's look at an example that's like a 3D game. You're going to process 1 million shapes. It's running in 60 hertz, so the frame time is 16.7 milliseconds. The OOP version is 25 times slower, but it's still hard to provide intuition about what do these numbers mean. Let's look at them relative to a frame. The OOP version, we're going to spend 88% of our frame processing the shapes, and the AVX version is 3.6%. In this case, Casey is exactly right. Even if you put it in another thread, it sounds like that is a big chunk of the CPU's work devoted to this, what potentially is a relatively small task in our overall game. Whereas 3.6%, it depends on your budget, if you're going to set a budget, but it just starts to sound a lot more tractable. I think Casey is exactly right in this case. If you need to process 1 million shapes in a frame, the OOP version is basically like, we don't have a game here. And the AVX version is like, we could ship this game. But let's look at another example that Casey did not show. Let's imagine a puzzle game like Candy Crush, and you're only going to process 100 shapes per frame. Again, we're going for 60 hertz is 16.7 milliseconds. This time, the times are obviously much smaller. These are microseconds. Let's look at the percentage of frame. The OOP version is 0.01%. That's 1 part in 10,000. You've used 1/10,000th of your frame to process the shapes. In this case, the OOP version is overwhelmingly fast enough to process this number of shapes. If you're making this game and you think you're going to process around this many shapes, the OOP version is perfectly fine, and spending any time optimizing it is not going to be worthwhile. Now we're going to do it slightly different. We're going to give us a budget of 1 millisecond. How many shapes can we process in 1 millisecond? Obviously, we can do the 100 shapes because we just showed that. And we can do up to 10,000 shapes, and we can in fact do up to 67,000 shapes. 100,000 shapes, 1 million shapes, and 10 million shapes. What we see is N can range up to about 10,000, and the OOP version is perfectly fast enough to process them. But if N is going to be 100,000 or 1 million, only the AVX solution can do it in 1 millisecond, and neither can do 10 million in a millisecond. If you're wondering where the chainsaw comes in, we can say that if you're worried about nanoseconds, particularly single-digit nanoseconds, the OOP version has too much overhead and it's not a good solution. However, if you even go to microseconds, that's 1,000 times bigger, 1,000 times longer, the OOP version is reasonable, and milliseconds and seconds, the overhead is extremely small. How does that compare to a chainsaw? A chainsaw is a tool that's useful for a lot of things. A lot of homeowners have a chainsaw, but it's not good for everything. I'm going to say emphatically that a chainsaw is not good for abdominal surgery. I'm talking about like an appendectomy, a splenectomy, bariatric surgery. Really anything that involves chainsaw touching human skin is probably a bad idea. But a chainsaw can cut tree limbs, it can cut small trees, and it can cut large trees. My summation of Casey's post is he's basically taking a chainsaw into the operating room. He's performing abdominal surgery. When it doesn't work out well for the patient, he stands up on the operating table and gives a speech and says, chainsaws are no good for any use, no matter what. Again, he's exactly right that for that use, the chainsaw was inappropriate, but he's exactly wrong because the chainsaw is perfectly usable in many other situations. Nothing is good across all space and time. What about death by 1,000 cuts? This is an objection that all of my loops are small, and yet I have so many of them, they add up to something large. This can absolutely happen. It depends on the structure of your application. If you don't know the structure of your application, if you don't know how many times things are being called, you should figure that out. You should do profiling. If you want to be defensive and make everything hyper-optimized, that's your choice, but I would be cautious about doing that. Now, if you think they're actually going to change your game from a puzzle game to an intensive 3D game, I think that's an unusual situation. Shouldn't be fearful of that happening. One of the values of extreme programming is courage, and I think it's for reasons like this. That you don't want to live in fear that I'm afraid the requirements are going to be changed completely out from under me at any moment. Let's start looking beyond just clean code. Let's amp that up to the generic amount of overhead that's 100 nanoseconds. This might be because you're using a slower language like Python or JavaScript, or it could be really overhead from any other source. So yes, this is a lot bigger overhead we're about to talk about. Here is an overhead of 100 nanoseconds on loop bodies of different sizes. If it's a 2 nanosecond loop body, 100 nanoseconds is going to completely kill you, right? But if we just go up to 2 microseconds, it falls way down. 5% starts to sound like a slightly annoying tax, but it's not horrible. As soon as you go to milliseconds or seconds, the 100 nanosecond overhead just completely disappears. I'm going to state the most obvious thing I could state here. 2 seconds is a billion times bigger than 2 nanoseconds. This is 9 orders of magnitude. And we as humans are not necessarily good about thinking 9 orders of magnitude in time. It's understandable that if you're fixated on one of these timescales, you might not be facile at thinking about the other timescales. If you think about concepts in computing that have a numerical size associated with them, like disk blocks, network packets, virtual memory pages, cache sizes, cache lines, I/O buffers, all of these sizes are tuned so that the amount of overhead relative to the amount of work done is acceptable. How about bites of a sandwich? If you were to chew and swallow after every cubic millimeter of rye bread, that would be horrible eating performance. Instead, we choose a bite size that's bite-sized. We mentioned that Casey worked at Rad Game Tools. They make game libraries. There's also the concept of game engine. Rockstar has a game engine called Rage that they're using to make Grand Theft Auto 6, and they've been using for the last 20 years. Game libraries and game engines tend to be highly optimized because they don't know what the game is going to be that uses them. But games also have a lot of what they call game code. The game code is specific to that game. In GTA 6, most of the developers are not working on the game engine. They're working on the missions or the levels. Because it's much less performance critical, a lot of times this game code gets shunted to a scripting language or a slower language. Back in 2005, I was working at Harmonix when we did the original Guitar Hero for PlayStation 2. And we used exactly this approach. About 2/3 of the game was written in C++, but 1/3 was written in a scripting language. The syntax looked like Lisp. It could contain data like JSON, but it could also have script commands. When you reach the end of a song, the engine would fire an event saying the song had ended, and you could attach a script that would do something like cause the track to explode or cause the characters to act a certain way. We had artists and designers could iterate on things completely without the involvement of programmers, without recompiling the game at all. This game was developed in 9 months from start to finish, and there's no way we could have done it if we didn't have both languages in play. But this idea of multiple languages with different characteristics cooperating happens far and wide outside of game development. Python is one of the most popular languages in the world, and the most popular for machine learning applications. How could this be when Python is known to be a pretty slow language? If you write something in pure Python like a matrix multiplication using Python lists and dictionaries, it's going to be incredibly slow, potentially 10, 100, I've seen even 1,000 times slower code in Python. But that's not what you do. You defer to dependencies which themselves are implemented in C, C++, Rust. Some of these dependencies are almost 100% Fortran even, but they run at full optimized speed. This allows different types of programmers with different emphasis in their career to all productively cooperate on a big complex problem. Here's an illustration of what a hyper-optimized library would look like. So maybe the actual machine learning kernel that just does tons of matrix multiplies. Everything is optimized. There's no overhead bigger than a nanosecond. Now, if you write something in pure Python with no fast dependencies, it's going to look more like this, where you're going to have a range of overheads that's quite significant, and you're not going to be able to do nearly as many operations. Finally, this is what I most commonly see in the real world, where you have the slower languages doing a less amount of work, but they defer down to fast languages. X is log here, so these faster languages are doing millions of times more operations. Casey used AVX in his optimizations. If you want to read about them, there's this convenient 5,000-page PDF from Intel you can dive into. Then you can read about how these chips are manufactured, how do the individual transistors work, how do they build the machines that are then used to make the chips, how do they mine the raw materials. There's no top either. Data centers that have hundreds of thousands of machines using billions of lines of code, where each individual machine is extremely complex. And if you're building an application that runs in the cloud, you're building this whole thing up even higher. There's a great postscript to Uncle Bob and his clean code book. I heard him describe this on a couple interviews. He really became enamored with the book, The Structure and Interpretation of Computer Programs. It's a famous book. It lays out from first principles how to write code, and it uses Scheme, which is a Lisp variant, as the teaching language. Uncle Bob fell in love with the book, and he fell in love with functional programming. He's mostly using Clojure. Clojure is a JVM language, which means if you write something in Clojure, you can easily call into Java. For the last 8 years or so, he's been writing a lot of functional programming. And he hasn't disavowed OOP at all. He's just said that these are both valid approaches, OOP and FP, which I think is a very sane and pragmatic approach that doesn't require slagging on someone's life's work. OOP is not a layer, it's a tool, and it's a tool that can be used in many situations, but not all situations. When I was a research engineer at UNC, Fred Brooks, who's a Turing Award winner, used to pop in on the research meetings and give advice. In his book, The Mythical Man Month, he wrote, "The programmer, like the poet, works only slightly removed from pure thought stuff. He builds his castles in the air, from air, creating by exertion of the imagination." Of course, Fred Brooks is right. We create castles in the air, but then we have to code them into bits. Not ethereal bits, not platonic bits, but real physical bits. Like magnetic domains on a hard drive, electrical charges in floating gate transistors inside an SSD, tiny capacitors in RAM, optical pulses on a fiber optic cable. At any given time, like right now, you could combine every physical bit on the planet, stick it into a dense, contiguous array of data, and interpret it as a single integer, one number representing the sum total of all software on the planet. We are all cooperatively contributing to this one number. This leads to two intriguing questions. How big will this number get? And what was the previous high score? Summary. You can write bad code using any methodology, any language. You can write good code using any methodology, any language. Let's take back clean code to mean good code, as it always did. OOP is good for many use cases, but not tight inner loops. You can read the article at tobeva.com/clean. This is Philip Winston. Thanks for watching.